I don't think I actually uploaded the last one, but I gotta remember to do that. But we'll go ahead and record today.
Yeah. And I think there was one more question that we didn't get to yesterday, number 7. So,
Okay. Number 7. Let me screen share here. Ah, yes. Several people had questions about this one, and it's definitely a challenging one. Mostly because, first of all, you have to realize how this is related to electric field, and then you have to actually extract some information from this graph. So from the things that we've learned about electric field so far, the things that we know about electric field compared to the potential is that we know that electric field always runs perpendicular to the potential, and electric field will point in the direction of increasing potential. So our electric field is actually going to be pointing something like this in this direction. That's perpendicular to the potential ish, and it's pointing in the direction of increasing potential because it says here that the equipotential lines increase by 500 volts for each line to the right. So this is definitely the direction that our electric field is going. If we wanted to represent our electric field in this region, we might do something like this. And so that's one thing we know about electric field. We can also assume that the electric field is constant, or it's uniform in this region, because these lines are all parallel to each other. If you have curved lines, then these lines would start to do this, and the distance between these lines determines the strength of the electric field. But because they're all parallel, we get parallel field lines, which also suggests that we have a constant or uniform electric field through here. So that's another thing that we know about it. And then the thing that we learn about, another thing we learn in this particular chapter about electric field and potential, is that you can actually calculate the magnitude of the electric field using the potential. The magnitude of the electric field is negative the potential, negative the change in potential actually, over the change in distance. We'll use change in R. And that's one of the things we learned in this chapter. And it's easily forgotten, I think, because it's such a simple equation that we tend to concentrate on the really complex things instead of this. And so what would be our change in voltage, first of all, and what would be our delta R? Well, it kind of depends on how far you go. If you go further, you're actually going to change your voltage more, and your delta R is different. And so what we would like to do is go as small a distance as possible. Well, I guess it doesn't really matter the distance you go, just make sure that you get it done. So, but I'm going to go as small a distance as possible, just because it's going to make more sense to me. So if I pick any spot along here, if I pick this spot right here, for example, and I zoom in on this part of the graph, I get something that looks like this. So here's my axes coming in here, and I have this electric field line that's going this way. And right in about right over here is where the 2 mark is, and right about here is where the 1 mark is. So that's 1 meter essentially right there. So this distance right here is 1 meter. However, I'm not moving in this distance. I want to move along this distance. I need to know how far this is right here, because between this line that's right here on this on the origin and the line that goes through the 1 meter mark, sorry, the line that goes through the 1 meter mark right there. I need to know this distance here because I know this change in voltage. The change in voltage between this red line and this red line, they tell me it's right here. It increases by 500 volts. So I know delta V all of a sudden. Delta V is equal to 500 volts, but I don't know delta R yet. Delta R, this is the 1 meter mark here, but delta R doesn't quite go out that far. It's a little bit less than 1 meter. What is it? Well, it's the side of this triangle here. We got this triangle that looks like this, where I've got a right angle up here. I've got a smaller angle right here, and I've got this side is equal to 1 meter. That's what the triangle is that I'm looking at. So I know the hypotenuse. I need to know this angle. It turns out that this angle is the same small angle that we have between on this triangle here. If you do all the geometry, you'll find that this is the same, this is a similar triangle, and this angle is the same angle as this angle. So this triangle, I actually know 2 of the sides. I know that this side is 8 units tall and this side is 2 units. And so I can actually calculate this angle. I can use the tangent, the inverse tangent of 8 over 2, opposite over adjacent. No, that's not opposite over adjacent. This would be opposite over adjacent. It'd be 2 over 8. Sorry, it'd be the other way around. Opposite from this angle up here is 2, and adjacent to this angle is 8. So 2 over 8. And that will give me some angle, theta. Then I can use that angle theta in this triangle over here to calculate the side that I'm interested in, which is the adjacent side to that angle. So then I would take the cosine of theta times 1. Whoops. I left off the S of cosine. Oops. Let's try, there we go. Okay. So the S of the cosine is there. So I take cosine of theta times 1, which is the hypotenuse of this triangle. And that's going to equal the side that I'm interested in. That's going to equal my delta R, in other words. Then once I have these 2 numbers, I just plug them in up here. And I calculate my electric field. Now the first part is going to be that number. The second part, and because we have 500 divided by some number that's a little bit less than 1, we should get an answer here that's a little bit over 500. Then the second one is the angle with the horizontal to whatever. So here we've got some choices to make. The angle that I just calculated is the angle that it is from the x-axis, right? So if I use that angle that I calculated, then I would use above the horizontal to the right, because that's the direction the electric field would be pointing. So that's kind of how I would do this problem, is using the delta V that they give me, the change in voltage they give me, and then using the geometry to calculate the angle so that I can calculate the distance that we travel between those potential differences. Plug them into this equation.
Yep, that makes sense.
Okay. Good. I think the hardest part of this one is to figure out how to do R, or delta R. First of all, to remember which equation we're using, because it's such a simple one, we overlook it. But how to calculate that delta R. This equation also we wrote in this chapter. It's often written like this, where E is equal to delta V over D, or just voltage over distance. Also written as electric field times distance equals V. But these are all the same equation. Since we're doing this in 2 dimensions, I like to use the delta R to show that the distance can be off axis from one of the axes. But it's all the same equation.
So then in my case, with it decreasing as it goes to the right, it would simply just be a negative.
So if it's decreasing, as it goes to the right, that means that your electric field is actually pointing this direction. right? And so what will change is the direction stuff down here.
Because like I ended up getting those direction ones correct, and it's saying that above and to the right.
Above and to the right, and yours says that it decreases?
As it goes to the right.
Decreases as it goes to the right. And you used an above and to the right down here?
Mm-hmm.
Let's see, maybe I remembered this wrong. That's entirely possible. I often get that mixed up. Let me check the book. Let's check what it says in the book. Well, apparently I'm not using my mouse. Here we go. So in the book, potential energy. So here, electric field and potential. Oh, yeah, it's the electric field lines go the other way. And the potential, when your positive charge is next to the positive part creating the field, the electric fields always go the other way. I always do mix that up, but that's, so my field lines actually go the other way and yours go to the right. Let's see, where's my homework problem? Nope, that's not it. Here it is. So so yours would actually go to the right and mine would actually go to the left because the positive side is over here. I always end up doing my arrows towards my positive charges of my field if the positive charges aren't actually there for some reason. So mine would actually be, it is above the horizontal, but it is to the left for me. It's at an angle above this, but the direction is to the left. Thank you for pointing that out. And this actually illustrates something that is always good to remember about potential and electric field. So I'm going to erase all this. Does anybody need this anymore? Okay. If you have something like this where you have potential surfaces, these equipotential surfaces that are represented by these lines, and it's increasing in some direction or decreasing in another direction, what the increase means is that if I put a positive charge in here on the higher end of these things, that means I'm closer to a positive source for this field. So if I put a positive charge in here where the voltage is higher for mine, that means I'm closer to the positive source of the field, which means the electric field is pointing from that positive charge away from that positive charge, right, towards the other side. And that's essentially what a potential means, because when you bring these closer together, they have a higher potential to get energy. They're essentially getting a higher potential energy because they want to push apart from each other and create that, like that kinetic energy away from each other. So yeah, that's essentially the definition for voltage. So. And if I just remembered to think about that first, because you always have to think through these things because our intuition for electronics is not natural. So you always have to kind of think through it first and make sure that you're thinking properly to get your intuition kind of under control for it.
We had one other question on 11. We had talked about that before, but we don't have the distance between the parallel plates.
Rectangular plate with dimensions 36 by 18, the plates of plastic film between them. Yeah, the plastic film between them is 1 millimeter thick, so that's the distance between the plates.
Oh, okay, that makes sense then.
And remember, in this question, it only wants to know what is going to, what increases would help the weight go higher in height, right? So what things are going to make the weight go higher if you increase them? Your problem may say what things will make the weight go higher if you decrease them. And that, of course, changes the problem. All right. So any more questions on chapter 19? Do we have time left on the due date? It's due today, so you can still finish it up and turn it in. All right, good. Well, if there are no more questions in chapter 19, then I think it's time to move on to chapter 20. And that's good. Chapter 20. So here, and as we move on to chapter 20, we're going to move away now from electric field, and we're going to start talking about electronics, how electronics or how electrical circuits work. And this is, I think, good for most people because this is something that we can connect some things to it, that some analogies or explanations or whatever you want, however you want to think about them, to things that we have more intuition for. It starts to be a little more practical, a little more easy to get a feel for these things. So electric current, resistance, and Ohm's law. So they have this great picture on the front that shows one of the analogies that we'll make use of, which is the flow of a fluid. We often see water flowing along rivers, or in this case, over a dam, the spillway of a dam. And you know that a river flows downhill, and it flows because it has potential energy at the top of the hill upriver that turns into kinetic energy downhill, downriver, right? And that's illustrated very nicely here with this dam. If you can imagine this water moving, I'm sure that you could imagine the water moves fairly slowly as it goes over the spillway, but it increases its velocity very quickly, accelerates very quickly. And then you can see the result of that. It even gets quite blurry out in here places where the water is moving extremely quickly, quicker than the camera can capture very well. So you're changing this potential energy into kinetic energy. Similarly, with electronic circuits, we can turn potential into movement of charge, which we call current. And potential measured in voltage, current is measured in amps or amperage, sometimes it's called, amperes. So you have that analogy to go to, a flow of fluids versus flow of electricity. And it's a very good analogy. So it works out fairly well. So first off, we're going to talk about current. So current is defined quite literally as the amount of charge over time. So you have a change in Q over change in T, right? Electrical current. Electrical current is measured using the unit amperes, coulombs per second, named after a famous physicist again. This one, a French one. There's a lot of French. We call him the dead Frenchman. He's one of them. André Marie Ampere. And many of the people that worked on electronics and electrical circuits lived in the 17 and 1800s. That was kind of the heyday of electrical and magnetic research. And it lasted, it really kind of went all the way into the 20th century. Actually, the study of electrical stuff started in the 1700s, even before Ampere was around, with people like Benjamin Franklin and others in Europe as well. And it went all the way to Maxwell, you could say, Clerk Maxwell, who lived in the late 1800s, early 1900s. So quite a long time. And also Faraday and others who lived in the 1800s. But this is named after him, that 1 ampere equals 1 coulomb per second. And that's actually a lot of current. Most things that we deal with, most things that we work with in our everyday lives have much less than 1 amp of current. 1 amp of current is a considerable amount of charge flowing. Just about the only thing that you deal with on an everyday basis that is drawing that much current or more. Your car draws that much current when it's starting. So the battery drives that much current through the starter motors when it starts. And bigger devices in your home, like the oven in your home, the vacuum cleaner in your home, oven, vacuum cleaner, perhaps probably the stovetop does, and the heater and air conditioner probably draw that much current, but not much else. It's a lot of current. So most things are drawing fractions of an amp or even a milliamps, thousandths of an amp, or microamps, even like your cell phone. The amounts of current flowing around your cell phone are very, very low on kind of the microamp, milliamp kind of range. So anyway, we have to think of a flow though in 3 dimensions, because it is in 3 dimensions. You are going to have current flowing through space in some way. Usually it's flowing through a wire in some way. And so they show a wire, a cross section of a wire here, kind of a cylinder representing a copper wire maybe, and charge flowing through it. And it's flowing through this cross-sectional area A that we have here. And we can actually break down the flow as it goes through there. Here they actually are going to actually calculate the amount of current. You have a truck battery, 720 coulombs of charge in 4 seconds while starting an engine. Well, you divide that 720 by 4, you get 180 amps, which is not unheard of for a truck. Cars are usually quite a bit less. In part B, we're going to calculate the amount of charge going. We have 1 coulomb of charge flowing through a handheld calculator that has 0.3 milliamps of current flowing. So how long do you have to use your calculator before it has 1 coulomb of charge going through it? Well, we just solve the equation for time, and we get time equals charge over current. 1 coulomb over 0.3 times 10 to the minus 3, 0.3 millicoulombs. Sorry, 0.3 milliamps rather, is 0.3 times 10 to the minus 3. And we get 3.3 times 10 to the 3 seconds, right? So you'd have to use your calculator for a whole hour to get 1 coulomb of charge to go through it. So here's a very simple circuit using current. We have a battery and we have a headlight and wires connecting them. Headlights and many other elements in circuits are considered resistors. And we use a symbol for a resistor. It just looks like this jagged thing here. So the headlamp is being represented by a resistor. Oftentimes when it's not a resistor for resistor's sake, we put a circle around it and maybe indicate that it's a lamp or a bulb or something, because there are things put in circuits that are just there to resist the current, and that's why they're called resistors, is they just push back against the current. They don't want the current to flow through. So the batteries are represented by voltage sources, I guess in general, are represented by 2 lines in the circuit, one longer than the other. The longer one representing the positive side of the voltage source, the shorter one representing the negative side. And so this is the circuit diagram for this lamp battery circuit with the wires. And wires are represented just by lines, just by these just plain old lines here. In a circuit like this, the very simple circuit with just a resistor in it, the resistor will resist the current flowing, but will not stop the current from flowing. And the current will flow from the positive around the circuit to the negative in this very simple circuit. That is not always the case. Current does not always flow through every circuit from positive to negative. We will see some instances where it goes the other way. But it does this in this case. Okay. So why does the current flow? The current flows because there is an electric field. Now, in the previous chapters, we've told you that electric fields inside of conductors are zero because they cancel each other out. All the charge is on the edge of the conductor, and so all the fields point towards the center and cancel each other out. But that is not the case if the charge begins to move. If the charge begins to move, then the electric field is actually going to be pointing in a particular direction and is going to have a particular value inside of that conductor. So in a wire that has charge moving in it, the electric field is the thing that's causing the charge to move. And here we have an electric field that's pointing to the right, which would exert a force on positive charges to the right. But positive charges don't move in metals very easily. Electrons move very well in metals. So what really happens is this down here. You have the electric field pointing to the right, and the electrons go the opposite direction from that. They go to the left. So whatever direction the electrons are moving, the current is actually moving the opposite direction. And again, that's thanks to Benjamin Franklin, who decided that he would call the electrons the negative charge. If he had called them the positive charge, then all the things that we defined after that, we would have had current be our moving in the direction of the electrons instead of in the opposite direction. It's confusing, but it's just because of a choice that Benjamin Franklin made to call the electron the negative charge. He couldn't tell, and he couldn't tell which was moving, so it's not really his fault. So current is actually the flow of positive charge. So whichever way the negative charges are moving, the current is moving in the opposite direction. So if we go back to this battery lamp circuit, we have a battery that has a positive terminal here that has a positive voltage here and a negative voltage here, relatively speaking. This, in other words, is the lower potential, and this is the higher potential. And positive charges are repelled away from higher potentials towards lower potentials. So the positive charges in this circuit, if they could move, would go this way. So that's the direction the current is flowing. What's actually happening is the electrons, which actually get repelled from lower potential things to higher potential things, towards higher potential things, are going this way. So the electrons are going this way, the current is going this way. We kind of ignore that when we talk about current because we can't tell the difference anyway. So we just say the current is going from the positive towards the negative in this particular circuit. And it's going, of course, clockwise. So let's actually use the current to calculate the number of electrons moving through the calculator that we had earlier. We have the current is 0.3 times 10 to the minus 3 coulombs per second. And here they're labeling it as the current of the electron. So that's actually a negative on there because it's a negative amount of charge. So they're saying the current of the electrons is this thing. How many electrons actually move through there? Well, we know the current. For this equation, the current is on the left and then delta Q over T. We want to actually calculate, so current equals delta Q over T, and that's our negative 3, 10 to the minus 3 per second. And then we're going to set that equal to the, let's see, they're not doing this the way I would do it. I should look before I leave. So they're actually going to just make a conversion here. So this is charge per second. We're going to make this into number of electrons per second by multiplying by this conversion of 1 electron per negative 1.6 times 10 to the minus 19 coulombs coulombs of charge. So this is electrons per charge. This is how much charge we have. When we multiply that, we get a number of electrons per second. So it's 1.88 times 10 to the 15 electrons per second for a current of 3 times 10 to the minus 3 amps. So that's a lot of particles. That's a small current, but that's still a ton of electrons. It's just a lot of electrons. Now, the interesting thing about movement of charge that we have been able to learn, even though we can't see them technically, we have learned that they don't really move in a very organized fashion. They actually move very randomly. So while some electrons will be moving super fast in a particular wire, some will be moving super slow, while some will be moving in the direction of the current, some will be moving in the opposite direction, some will be moving perpendicular to that direction, going around and around in the wire, or on the outside of the wire, doing all kinds of weird things. There's kind of random movement going on, but the average velocity of all these particles will have something to do with the current moving forward. And that average velocity, we call it the drift velocity, is essentially the movement of overall charge. The electrons also don't just go from one end of the wire to the other. What usually happens is they go for a little while and then they run into another electron and get bounced backwards. But they push that one forward and it pushes the next one forward and it pushes the next one forward. So it's kind of like dominoes. We start current going through a wire and it's like starting dominoes. You hit the first domino and it might it's not going to get very far down the wire, of course, down this row of dominoes, but it does affect the next domino, which affects the next domino, and it's a very rapid chain reaction that happens. In fact, electricity moves close to the speed of light because of this chain reaction kind of effect. It moves very, very quickly. So when you turn on that light in your room, it comes on it seems like instantaneously. It is slightly after you flip the switch, not only because you had to flip the switch, but because the current had to actually make it down to the other end and it had to actually heat up the light bulb or do whatever it needs to do to the light bulb, depending on the kind of light bulb you have these days to make it light up. But anyway, it's still a very, very fast thing. And because of this domino effect that comes from the fact that they don't move just from point A to point B. That's just not how electrons do it. There's too many other electrons in their way. But it turns out to be a good thing because it allows it to move much faster in this chain reaction kind of movement. So this drift velocity is this overall forward change or movement of charge, not necessarily of a single charge, but of the overall charge. It's kind of an average overall charge movement. You could think of it as forward. And as it moves and it goes past other electrons and interacts with other things in the metal and other things around it, there is some energy loss. Some energy is lost. You could think of it almost like friction. Two electrons, as they go past each other, repel each other, and that pushes back on them, and that's kind of like friction. And this can turn into heat in the metal. This can create a fair amount of heat in the metal, and the metal radiates that heat outward, and then that energy is lost to the system. And that is very common in electronics. It's very common to lose energy in your system. In fact, it has a lot to do with how well the electronics work. If you can bleed that energy off very quickly and very efficiently, your electronics will work better. But if you don't, that heat gets stuck in the electronics and it makes the electrons in the electronics more and more random. And eventually you get to a point where nothing moves very well, no signals move very well through your electronics, and that's not a good thing. So this is one of the reasons that laptops have fans on them sometimes, or that when you're working on your phone for quite a while, watching a video, you can actually feel that it's heated up a little bit. When the computers have to do things for a fairly long amount of time, that dissipated energy that becomes heat, you can feel it, you can notice it, you can do things with it if you need to as well. So there's always a heat loss in the normal conduction of electricity. This is actually used to great advantage in incandescent light bulbs. They put a resistor in there that glows when it heats up, and then you can get light out of it, which is great. There is an equation that can actually relate the drift velocity to the current. So if you have a certain amount of current in certain situation, you can calculate that drift velocity. And we actually talk about it in more detail later on, but here they give us the equation, and it ends up being fairly complex. You have this q, this n, this a, and this x and delta t, and all of it is important. A is the cross-sectional area of the wire, that circle of the wire if the wire is a cylinder. X is the distance that the charges travel through that wire in any given time. Time is, of course, the time that goes by. And then N is the number of charges, I believe. It's the number of free charges. And sometimes they use N as the number of moles of free charges, but usually that's capital N. In this case, little n is the actual number of free charges. And so actually it's the other way. Capital N is usually the number of charges. Little n is usually the number of moles. But in this case, they're using N as the number of free charges that's actually in the volume of the wire that we're interested in. What do I mean by the volume of the wire? Well, here is that cross-sectional area. If these charges move some distance x through here, this is the end of that distance x, the dotted line. This is a cylindrical volume of wire. So this calculation takes that into account. It takes the area, it takes the number of charges in the area. Let's see, where did it go? I lost my equation. Drift velocity. There it is. Takes into account that area, takes into account the drift velocity through that area, the charge. So the Q is the charge of the individual charges, since they're electrons, be the charge of an electron, or if it's a proton, be the charge of a proton, which is the same as an electron. And then N being the number of those charges. So if you multiply the number of charges by the amount of charge in each charge, by the area, or the area, that the cross-sectional area of the wire, times the velocity, the drift velocity here, you can get the current. Hopefully that makes sense. But that's another way to calculate. That's one way to calculate the current. It's not a definition of the current. It's a way to calculate how many charges are moving through that volume in every second. Where is the time in this equation? Well, it's in the velocity. The velocity is a distance over time. So it's this distance, or how much time it takes to go that distance in the end. So let's calculate the drift velocity in a common wire, right? We have 12 gauge copper wire, diameter of 2.053 millimeters, 20 amp current. And we're saying that there's one free electron per copper atom. So that's important. Remember, we said the number of free electrons is Q here. Or sorry, is N. Right. And then Q is the amount of charge on each carrier. So we're going to say that's the charge of the electron, 1.6 times 10 to the minus 19. And then we need to figure out the N number of charges that are carrying the charge. How many that are carrying the current. Well, okay, let's figure out how to do this. We know cross-sectional area. We know this distance here. So we know this volume here from this problem. Dang it. Keep missing the problem. Yep, this is it. Okay. So we're back here. We're back to our problem here. So we want to first figure out the density of free electrons in copper using the things that they've told us. They also give us some things from the periodic table. The density of copper is 8.8 times 10 to the 3 kilograms per meter cubed. And the atomic mass of copper is 63.54 grams per mole. This mass here, this mass per meter cubed, the density, we have a mass divided by meters cubed. We've got here a atomic mass in grams per mole, and we're going to figure out the number of free electrons from these two numbers, also including the number of atoms in a mole. because the number of atoms in a mole combined with this atomic mass of copper is essentially going to tell us the mass of, it's going to tell us the number of atoms of copper there are per unit, per meter cubed in copper. So we calculate that number right here. So that's the number of atoms that are in this, and we know that there's 1 electron per atom, so that's also the number of electrons that are free in per meter cubed of copper. So that's our N right there, number of charges available. And then we're going to calculate the area. It's just pi r squared. They've given us r, well, they've given us d diameter, so we take diameter divided by 2 squared multiplied by pi, denote that area. Then the drift velocity we calculate using the formula, solving it for the drift velocity, current over n times q times the area. And it turns out to be negative 4.53 times 10 to the minus 4 meters per second. So why is the negative there? The negative is there because that's telling us that the current wants to flow, the current normally would flow one way. In this case, it's flowing in the opposite way that it normally would. That always is the case if you end up with that negative sign in there. Unless you've done something wrong in setting up the problem, I guess. But, then we're multiplying by the charge of the electron here. And we're multiplying by the cross-sectional area in the denominator here. So 20 amps divided by those 3 numbers gives us our value. All right, so so you can see here that the drift velocity is actually not that big, but the signal is much, much bigger. It's close to the speed of light. So even though the average electron's not moving much, the signal can. Are we done? I think we're done.
Yep, we're just about out of time.
Okay, so we'll come back to this on, let's see, what is today, Tuesday. We'll come back to this on Thursday, and then we will miss class on Friday because of my meeting, and we'll be back next week. Have a good one.
All right, thanks, you too.
Are we gonna have a lab tomorrow?
Yes, we need to figure out when we're going to do labs. When were we going to do that?
11 a.m. I think.
Mondays? At 11? Wednesdays at 11, yeah. Yeah, come in tomorrow at 11 on Wednesday, and we'll do your lab then.
Okay.
See you then.